So in this video, what I would like to do is work through the ALEKS objectives for this week. So I'm going to do one example of each objective type. There are 14 objectives this week, so hopefully you're doing 2 or 3 a day. And there are 2 major topics, mainly the first one being the development of the modern atomic theory, and in particular the atomic theory being expanded via Schrödinger's equation to be able to deal with multi-electron atoms. And then the second major topic that we're going to be dealing with is periodic properties of the elements. And we look at a couple of periodic properties. We look at atomic and ionic radii, we look at electron affinity, and we also look at ionization energy. So first of all, we're looking at understanding the meaning of the de Broglie wavelength. So every particle has a wavelength associated with it according to de Broglie, and that wavelength is given by that formula. And if the wavelength of the particle is larger than the diameter of the size of the object, it might not be the diameter, it might not be spherical, then the object will display, or its properties will be dominated by its quantum properties. Right? That they will be the most important properties of that particle. Now, if the wavelength is very, very small, smaller than the size of the particle itself, then we're not going to see the quantum properties. We're only going to observe the classical everyday properties of the object. So in this problem, I bet you that that's what this is all about, but the devil is in the details, right? So what we're really asking ourselves is the wavelength bigger or smaller than the size of the particle? Now let's see what they've got. It says, imagine an alternate universe where the value of Planck's constant is a little different. Instead of it being 10 to the minus 34 joules to the second, it's going to be 6.62607 by 10 to the minus 7 joules seconds. Okay, so we're going to have to keep that in mind. In that universe, which of the following objects would require quantum mechanics to describe, that is, would show both particle and wave properties? So what we're kind of asking here is, for which of the following is the wavelength bigger than the size of the object, right? And then the quantum properties are going to dominate, and you have to use quantum mechanics to describe its properties. And then what ones are going to act like everyday objects, which means that the wavelength is less than the size of the object. Now, I can't use radius because they're going to be things, or diameter, because there's things like cars and mosquitoes and stuff in there. So we know that what we're going to have to do in every case is calculate the wavelength using the de Broglie formula. The thing that we have to keep in mind is Planck's constant is going to be a little bit different, 6.62607 by 10 to the minus 7. Whenever we use the de Broglie formula, or formulas in general, mass is going to be in kilograms, not grams, and then our velocity meters per second. So sometimes you have to do a little bit of unit conversions before you're going to get your wavelength, right? So let's see what we've got here. So it says a car with a mass of 1600 kilograms. So that's mass in kilograms. That's good. It is 5 meters long. We're going to use that for our comparison. But the velocity is given in kilometers per hour, and we need the velocity in meters per second, or our equation isn't going to work. So my first thing is to get my velocity into correct units. So 140 kilometers every 1 hour, and I know that there in 1 hour there are 60 minutes, and in 1 minute there are 60 seconds. So that takes care of the hours problem. And then now we just got to do the kilometers, and I know that there are 10 to the 3 meters in 1 kilometer. So that means that my velocity here is going to be 140 times 1 on 60 times 1 on 60 times 1 by 10 to the 3. So in meters per second, this ends up being 38.88888, right? 38.889 meters per second. So we're ready to go because we've got our Planck's constant, we've got our mass in kilograms, and we've got our velocity in meters per second. So Planck's constant, or wavelength, is equal to Planck's constant divided by the product of the mass and the velocity. So 6.62, we've got to get all those digits there, 6.62607 by 10 to the minus 7 joules seconds. Now, if you want, you can rewrite joules in a different kind of way. Joules is kilograms meters squared, seconds to the minus squared, that's my joules seconds, there we go, divided by the product of, now the mass was 1600 kilograms, and the velocity, we just calculated it, 38.89 meters seconds to the minus 1. Whew! Alright, we got this, So kilograms goes, meters, and one of the meters goes, and then we've got seconds to the minus 2 times by seconds, so that's just going to become seconds to the minus 1, and then seconds to the minus 1 second ones, and all we're left with is meters. So we know we got our dimensional analysis correct, so that's going to give it to me in meters. Don't forget to use the modified value for Planck's constant. So 6.6267, second function, 10 to the minus 7, divide, parentheses, 1600 kilograms, and then the velocity was my answer from before. So I just go answer, close parentheses, and away we go. And this is going to give it to me in meters. So it is 1.06 by 10 to the minus 11 meters. So that's a small number, isn't it? Now, how big is my car? Well, my car is 5 meters long. So it's like, 15-foot long car, right? So this number here is less than 5 meters. So the wavelength is a lot smaller than the size of the object. So a classical description is what's going to work for that. We don't have to use quantum mechanics to describe how it behaves. So rinse and repeat for the other 3 options, right? But we might have some different unit conversions depending on what's going on there. So let's have a look here. So remember, we need our mass in kilograms, and it says a mosquito with a mass of 1.6 milligrams. There's your problem, right? So the milligrams are going to have to go to kilograms, and then this is 11.6 millimeters long. That's just for comparison to our wavelength, but at the end of this, we're going to have to turn our wavelength into millimeters in order to make the comparison. And then it says moving at 1.2 meters per second, and we want our velocity in meters per second, so it all looks good. So the only thing I've got to do here is turn my milligrams into kilograms. So 1.6 milligrams times 10 to the minus 3 grams per 1 milligram times 1 kilogram is 10 to the 3 grams. So here we go. Calculator, 1.6 times 1 by 10 to the minus 3 times 1 divide 1 by 10 to the 3. Ooh, that's not good. Didn't get the second function in there. Second function. There we go. All right, there it is, 1.6 by 10 to the minus 6. could have done it in our heads, couldn't we? Kilograms. Okay, that makes sense because there's like 1/1,000,000th of a kilogram in a milligram. All right, so we're all good there. We knew we had it anyway because our units worked. All right, so we got our mass in kilograms, and so now what we've got to do is just use the de Broglie formula and then compare that to what the actual wavelength of our mosquito is. So lambda equals h on mv, 6.62607 times 10 to the minus 7 is the value of h that we're using, so it's not the regular Planck's constant, and then that is joules, which are kilograms, meters squared, seconds to the minus 2 per seconds, divided by our mass in kilograms, 1.6 by 10 to the minus 6 kilograms, times by our velocity in meters per second, which was 1.2 meters per second. So what happens? One of the meters cancels, one of the meters cancels, one of those guys cancels, the kilograms cancels. That leaves me with seconds to the minus 1 times by seconds, which is going to cancel. So ultimately my units will be meters. All right, so as long as everything's in the correct units, it's all going to work. So let's put our math in. 6.62607 by 10 to the minus 7 divide parentheses mass in kilograms 1.6 times 10 to the minus 6 times our velocity in meters per second 1.2 close parentheses, hit enter, and there it is, 3.45 by 10 to the minus 1 meters. 3.45 by 10 to the minus 1 meters. Now we're not done because we've got to turn that into millimeters to compare it to the length of the mosquito that was given. So we got 0.345 meters, and I know that in 1 millimeter there are 10 to the minus 3 meters. So what does that mean? That this 0.345 meters is 345 millimeters. So the wavelength is 345 millimeters, which is pretty big, right? 34.5 centimeters, in fact, which is obviously bigger than my mosquito, which is only 11.6 millimeters long. So that is greater than 11.66 millimeters, which means we've got to use quantum mechanics if we know anything about this system. So that is going to have to be described using a quantum mechanical model. And so on and so forth for all four of those things, right? So it looks like what we're going to have every time is perhaps a little bit of a unit conversion, and then we've got to apply the de Broglie formula. As long as you don't make a mistake, you keep track of all of your units just to help you double check whether you're, that you're not making errors, you should be okay. So it's kind of like a little bit of unit conversion, little bit of using the de Broglie formula. Now let's do another one just for fun. So it says here an atom with a mass of 1 by 10 to the minus 26 kilometers, kilometers, that doesn't make any sense, 82 picometers wide. 82 picometers. So we need to know what pico is, and pico is equivalent to 10 to the minus 12. So this is sort of like giving us the size of the whole thing, right? So that's going to be for our comparison. We don't have to convert our mass because it's already in kilograms. And then 155 meters per second, it's already in meters per second. So getting the wavelength is going to be pretty easy here, but I've got to convert it to picometers for the comparison at the end. So it's H on MV, so 6.62607 by 10 to the minus 7 joules seconds. I won't keep going through the dimensional analysis. Our mass has to be in kilograms. For this atom, it was 1 by 10 to the minus 26 kilograms. And then its velocity has to be in meters per second, and it was 155 meters per second. So the wavelength in meters, because the de Broglie formula returns meters, is going to be 6 0.62607. Second function, e minus 7, divide, parentheses, 1 times 10 to the negative 26 times 155, close parentheses, enter. So our wavelength, wow, is huge, right? 4.275 by 10 to the 17 meters. 4.275 by 10 to the 17 meters. Do you think that's bigger than our atom that is only a few picometers across? Of course it is, right? That's huge. So, wow, why is it so big? Because we're dividing by a tiny little number there, right? And that's going to make it really big. Now, if you don't believe me, we can now turn this to picometers. 1 picometer, we've got to be careful. It's a lowercase p, is 10 to the minus 12 meters. Remember, you get those decimal prefixes are given in ALEKS for you, so you don't have to worry about memorizing them. And so that's just going to end up being 4.275 by 10 to the 29 picometers. Okay, I won't go through that, which is very much bigger than the size of this atom. This atom was 82 picometers bigger. That is a lot bigger than 82 picometers. So that means that we have to use quantum mechanics to describe that atom. Okay, so the wavelength is bigger than the object itself. We're going to use quantum mechanics to describe it. Okay, now what about this turtle? Okay, interesting. The turtle has got a mass of 600 grams, and we're going to have to turn that into kilograms because we need to work in kilograms with the de Broglie equation. And then they give us the size of the turtle for the comparison. It's 29 centimeters long, so it's a fairly small turtle. It's not like a big sea turtle or something, right? Because they would be bigger, wouldn't they? And then it says that the turtle is moving, not surprisingly, at 2.3 centimeters a second. Because it's a turtle, it's going really slow. We're going to have to turn that into meters per second. So we've got a little bit of work here. The grams have to go to kilograms, so that's going to be easily enough to do. So 600 grams times 1 kilogram is 10 to the 3 grams. So that ends up being 0.600 kilograms. And then we've got this guy here, his velocity is 2.3 centimeters. I should do dimensional analysis. Centimeters every 1 second, and we need it in meters per second. So I gotta do meters, centimeters, 1, 10 to the minus 2, centimeters. So that means that he is doing 0.023 meters per second because he's a turtle and he's slow. All right, so that's kind of fun. Okay, so now we're ready to go. What we're going to do is we're going to calculate this turtle's de Broglie wavelength, because every turtle wants you to do that for it. And then we're going to see how that compares to the actual length of the turtle. So here's our alternate value for Planck's constant. And then we've got our mass in kilograms, so 0.6 kilograms. And then our velocity in meters per second, 0.023 meters per second. So everything is in the correct units. And away we go. We're going to get this wavelength. Now, we're going to turn this into centimeters, but the de Broglie formula to begin with will give it to us in meters. So the modified Planck's constant, or the alternate Planck's constant, I guess is actually the better one, 6.62607 by 10 to the minus 7, divided by the product of the mass in kilograms, 0.6 kilograms, times by the velocity in meters per second. There we go. Enter. And here's our answer, 4.80 by 10 to the minus 5 meters. 4.80 by 10 to the minus 5 meters. Now we need to turn that into centimeters, right? So the wavelength is going to be 4.80 times 10 to the minus 5 meters times 1 centimeter is every 10 to the minus 2 meters So this is going to end up being 4.80 times 10 to the minus 3 centimeters. So it's not even 1 centimeter, right? So the wavelength is a lot less than the 29 centimeters of the turtle, which means the wavelength is smaller than the size of the object itself. So we're going to be describing this turtle using classical mechanics rather than quantum mechanics. All right, that was a lot of kind of unit conversions and just kind of grinding through it, but, you know, totally doable, right? It just takes a bit. I pity you for having to do 3 of those in a row, because it's a lot of, you know, sort of like simple math again and again and again. Just take your time and, you know, have frequent breaks and you'll be okay. All right, finding the minimum uncertainty in a position or velocity measurement. So it sounds like it's going to be Heisenberg's uncertainty principle. So what we know is this: delta x times by the mass multiplied by delta v is always greater than h on 4 pi. Now, in ALEKS, m delta v, they describe that as being the uncertainty in the momentum, which is not entirely incorrect. We just haven't really learned, unless we've taken physics, that momentum is equal to mass times velocity. So don't get too hooked up on that, right? The P just indicates momentum, and momentum is just the product of the mass and the velocity. So I'm guessing we're going to be given some of these things. It says an atom of helium has a radius of 31 picometers. Okay, so we know it's 31 by 10 to the minus 12 meters is its radius. That's a length, isn't it? And the average orbital speed of the electrons is about 4.4 by 10 to the 6 meters. So velocity is 4.4 by 10 to the 6 meters per second. Now, obviously, there's a little bit of uncertainty in that. So, because there's always uncertainty in both position and velocity. Calculate the least possible uncertainty, here it comes, in a measurement of the speed. So we're going to be solving for what the uncertainty in the speed is. All right? And then it says, write your answer as a percentage of the average speed. Okay? So we'll do that when we get there. So what have we got? An atom of helium has a radius of 31 picometers. So okay, so this is what we have to do here. We have to reorganize this to solve for delta V. So first of all, I've got to bring everything other than delta V over to the other side. Okay. Now it says an atom of helium has a radius of 31 picometers. So where is the atom? All right, so there it is there. So we're going to call that position there. And 31 that way. And 31 that way. So it's somewhere in there, isn't it? It's in there. It's centered about that. So delta X is plus or minus 31 picometers. That's what they're giving you with that, right? You know that it's somewhere about, it's plus or minus 31 about that central position. Okay, that's the uncertainty in our position. So delta X is 31 times 10 to the minus 12 meters. That's what that is. Okay, we got that figured out. So it looks like it's good, except for we've got one missing piece of information, and that's the mass. And we need the mass in kilograms. Now, how are we going to get that? Well, this is where the periodic table comes in. So I'm going to go to the periodic table. Now, ALEKS is a nice periodic table. I'm going to go to the one from the book. The one that's in ALEKS is nice because it has the, you click on the element and it gives you information about it, and I like that. So 4.003 grams for a whole mole of helium atoms, right? So 4.003 grams for 1 mole of helium. Now we don't want for a mole, we just want for 1, and we also need it in kilograms. So what I know is that in 1 mole of helium, there are 6.022 by 10 to the 23 helium atoms. So that'll get rid of my moles, and then I need to turn it into kilograms, and I know that 1 kilogram is the same as 10 to the 3 grams. So in this way, I'm able to get the mass of a single helium atom in kilograms, which is what I'm interested in. So here we go. 4.003 divide 6.022 second function e to the 23 times 1 on 1,000. There we go. Alright, so they cancel, grams cancel, so yeah, it's going to give me kilogram per helium atom, isn't it? Right, there we go. Okay, good. So, and obviously it shouldn't be very much. So 6.647 by 10 to the minus 27 kilograms. That sounds similar to what we were getting before for the mass of an atom. So what we've got there is our mass. So if I look at this, Planck's constant is a constant. 4 is a constant, obviously. Pi is a constant. I've just got the mass, and I've got the delta x. It's the same as the radius. So it looks like we're ready to go and plug and chug. So the uncertainty in the velocity is going to be Planck's constant, and now it's the actual value for Planck's constant this time, 6.626 by 10 to the minus 34 divided by 4 pi times the mass, which was 6.647 by 10 to the minus 27, times by the uncertainty in the position, which was 31 times 10 to the minus 12, and that was meters. So at this point, I'm going to get the uncertainty in the velocity. It has to be, it's greater than whatever this is, and this is going to be returned in SI units, which will be meters. So let's see what we've got. 6.626 by 10 to the minus 34 divide parentheses 4 pi times 6. Oh, actually, we can just do this little shortcut here. We can use the answer from before, so we don't have any rounding area. There we go. Times 31 by 10 to the minus 12, and put all of that into parentheses. So there we go. Wow, that sounds like really big. Is this right? Okay. So, okay, 2.559 by 10 to the 2 meters. Wow. Oh, meters per second. There we go. That's better. Sorry, I was like, woo, because it's velocity, not delta x, isn't it? Sorry, there we are. So the uncertainty in the velocity is pretty big. It's at 255.9 meters per second. Wow, that's a lot. So, oh, then you realize how fast it's going. It's going 4.4 million meters per second. All right, so we need to take this number as a percentage of that. So 2.559 times 10 to the 2 over 4.4 by 10 to the 6 times 100. All right, I was like, wow, that's a really big number. But then you realize that it's not really that big. So divide 4.4 by 10 to the 6, and then don't forget the times 100 times 100. There you go. So it's not a very big difference, is it? 5.815 by 10 to the minus 3. 5.815 by 10 to the minus 3%. Okay, so it's a fairly small percentage. All right, there you go. So let's have a look at that. What did we do? An atom of helium has a radius of 31 picometers. What we realized is that that means that the uncertainty about its position is plus or minus 31 picometers. It's somewhere in this range, isn't it? All right? You can't put an exact number on it. It's somewhere in there. And then it says the average orbital speed was 4.4 by 10 to the 6 meters per second. And we realized that we didn't need to do anything with that number. It was good to go as meters per second. And then it says calculate the least possible uncertainty in a measurement of the speed, right? So we want to calculate what delta V is. So what we did was we reorganized the Heisenberg uncertainty principle to solve for delta V, and then we made sure our mass and our delta x were in correct units. So our mass was in kilograms and our delta x was in meters. Now to get the mass was a little bit complicated because we only have the mass of a whole mole of helium atoms. So we had to go through and turn that into the mass of one helium atom in kilograms, and then we were good to go. We did our plug and chug. Now it asked for the answer to be given as a percentage, and so we had to do that. And then we also need to round this to two significant figures, which I haven't done yet, but it would be 5.8 by 10 to the minus 3%. So there's not a lot of uncertainty in its velocity. Not a lot, but there is some. Okay. Now, deducing the allowed quantum numbers of an atomic electron. Okay, so n is called the principal quantum number, and it can take values of a positive integer. All right, so another way of saying what n is it's the shell number. Now, L can have different values ranging from 0, 1, 2, all the way up to a maximum of n minus 1. And L is called the angular momentum quantum number, but what it corresponds to is the subshell type. And in particular, L equals 0 is the same as an S subshell. L equals 1, you guessed it, is a P subshell. L equals 2 is a D subshell, and L equals 3 is equivalent to an F subshell. So S, P, D, and F, that's how it works, all right? Now, what do we have from there? Well, we also have ML, and ML runs from minus L in increments of 1 up to 0, and then it goes from 0 all the way up to plus L in increments of 1. All right, so it really depends on the value of L. So when L equals 0, the only possible value is from minus L, minus 0 is 0, up to plus L, plus 0 is 0. So the only value of ML is 0. All right, so it depends on the value of L. And then finally we have MS, and MS is plus or minus a half, and that's the spin quantum number. So we have the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. You can look these things up in tables. You just kind of got to know how to use them. So it says list all possible values of the angular momentum quantum number L for an electron in the n equals 3 shell of an atom. So when n equals 3, possible values for L would be 0, 1, or 2. So for an atom in the third shell, it can have an S, P, and D subshell. So we know that, right? For an atom in the third row of the periodic table, because remember the shell number is equal to the period number, right? For atoms in the third row or beyond, they can have an SP and a D, and we know that to be correct. All right, so the three values there, 0, 1, and 2. Counting valence electrons in a neutral atom. So the number of valence electrons is equal to all of the outer S and P electrons plus any electrons in a partly filled D subshell. Now that seems wickedly complicated until you realize that only transition elements have partly filled D subshells. So that makes it kind of like a little easier. Now for the representative elements, those are the ones that are in an A group. The number of valence electrons, and you know this hopefully from your chemistry 139 class, the number of valence electrons is just equal to the group number. So if it's in an A group, you get an easy write on this. So the representative elements are those that are in the A group. All right, so you don't have to worry about doing all of these things. So let's find lead in the periodic table and determine whether it's a transition element or whether it is a representative element. That's going to be our first thing. So where is lead? There's lead. Hallelujah. Lead is right there underneath tin. So lead is in group 4A, right? You have to use the A and B notation for this, right? So lead over here, well that's actually 3A there, so 4A is more in there. Lead is there, right? So lead is in 4A. So what that means is that lead has 4 valence electrons. Now what period is lead in? If we look at our periodic table, period 1, 2, 3, 4, 5, 6. It's in period 6. So let's go through the electron configuration for lead. It's going to be, or the outer electron configuration for lead. So it's going to be xenon, 6s2, yeah. Then we go all the way across these guys here, 4f14. And then we go back, 5d10, yeah, and then finally 6p2. Got that? Xenon, in parentheses, 6s2, 4f10, or 14, sorry, 5d10, 6p2. The D and the F are completely filled. We just said it's the outer S plus any partly filled D. So 2 plus 2, 4 valence electrons. So even if you write out the outer electron configuration and you add it up according to this rule, you're going to get the same as if you just use the group number for an A group. So, you know, either way works just fine. All right. How many valence electrons are in magnesium? Now, our rule that we had before about things just being equal to the group number if they're a representative element don't apply for ions. So we have to look at where magnesium is. There's magnesium there. Why don't we just grab this? We don't have to keep flipping over, do we? There we go. Okay. is magnesium, group 2A. It's got 12 electrons. So let's write the electron configuration out. It's going to begin with neon, and then we got 3s2. So that is the electron configuration for a neutral magnesium atom. Now we want for where we've taken one electron away. Magnesium, going to take one electron away to give you a single positively charged cation. So what electron's going to go? It's going to be that one, right? So when this guy becomes Mg+, we're going to take away one of those 3s electrons. So how many valence electrons has it got? Remember, valence electrons are outer s and p plus any partly filled d's. And this guy doesn't have any outer p's, but it has one outer s, so we get 1 for that, and it doesn't have any partly filled d orbitals. So it's got one valence electron. One valence electron, all right? Now, if you wanted to, you can write out the full electron configuration. So for neon is 1s2, 2s2, 2p6, and then we would, that's the neon part. It wouldn't make any difference, right? If you want to write out the full one, it's not going to make any difference because it's outer S and P plus any partly filled D, still going to give you one valence electron. Any partly filled orbitals are always going to be in the outer electrons, so you can get away with writing the condensed electron configuration. All right, let's move on. Just going to reboot this because it's lost connection with the server. All right, here we go. Draw the electron configuration for a neutral atom of zinc. So let's get our periodic table there. Here's our zinc. We need to get the electron configuration for it. So the element that comes before is argon. 18 electrons, and then we've got 4s2, and then we've got 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 3d10, and that is our neutral atom of zinc. There we go. Now what does it say? It says draw the electron configuration. So we better write out everything because it doesn't ask for the abbreviated one. So argon is the first 18 electrons, isn't it? Right. So you've got a couple of ways of doing this. You can use the Aufbau diagram. So I won't draw it all out. Or you can count it off the periodic table. I'm going to count it off the periodic table. So to helium goes 1s2, to beryllium 2s2, to neon 2p6, to magnesium 3s2, to argon 3p6, to calcium 4s2, and then we go across here and then 3d10. Okay, so that is the complete unabbreviated electron configuration, and I just counted it off the periodic table, right? Remember, these guys are NS, these one are N-1D, these are NP, and these are N-2F, and N just equals the period number. All right, so the electron that goes into beryllium here to finish it off is going to be 2s2. All right. The electron that goes in here to finish off neon, the last electron of neon, will be 2p6. The last electron that finishes off radon down the bottom here is going to be 6p6, because 6, and then we got p1, p2, p3, p4, p5, p6. All right. So you always kind of know this is period 6, this is period 7. So for europium, its last electron will be 6 minus 2, 4, 4f, 1, 2, 3, 4, 5, 6, 7. The last electron in europium will be 4f7. The last electron in lutetium will be 4f 14. And if I wanted to go to say like actinium, it would be 5F1 would be the last electron. All right, let's move on. Write the electron configuration for a neutral atom of gallium. Now, gallium comes underneath aluminum. That's that element that was the properties were predicted by Mendeleev before it was actually discovered. So we want to count off the full electron configuration. So to get to helium is 1s2, to get to beryllium is 2s2, to get to neon is 2p6, to get to magnesium 3s2, to get to argon 3p6, to get to calcium 4s2, to get to zinc 3d10, and then to get to gallium it's going to be 4p1. Remember, it is ns n minus 1d np and then n minus 2f. Okay, and then these guys are 6 and 7. All right, so that's the full electron configuration of gallium. All right, let's have a look at this one. Identifying the electron added or removed to form an ion from an S or P block atom. So that's just saying a representative, or sometimes it's called a main group element. So this is the S block, and this is the P block, right? And what happens is every time we lose an electron, so say I have lithium, and this guy loses 1 electron, my atom gains a +1. Now, every time an atom gains an electron, the atom will gain 1 minus. And so that's how it happens, right? We're going to add and subtract electrons in order to give them electrical charge, right? So what we've got to do is begin with an electron configuration, and then we're going to add or subtract the required number of electrons. So to make it a +1 cation, remember that cations are positive, right? To make it a +1 cation, we're going to do that. We're going to remove 1 electron, right? We're going to remove 1 electron. To make it an anion, we're going to add 1 electron, and it's only 1 electron because the number of electrons we add is equal, or subtract, is equal to the size of the charge. So helium is given by, hydrogen is given by way of an example, and then we're going to do it for neon. So neon, carbon, and calcium. There we go. So let's put this in there. So we've got neon, carbon, calcium. So let's write out the full electron configuration for neon. It's going to be 1s2 gets me to there, then 2s2 gets me to beryllium, and then 2p6 gets me to neon. So that's for a neutral neon. Now I'm going to do carbon, 1s2 gets me to helium, 2s2 gets me to beryllium, and then 2p1, 2p2 gets me to neutral carbon. And then finally calcium. So calcium, it's going to go 1s2 gets me to helium, 2s2 gets me to beryllium, 2p6 gets me to neon, 3s2 gets me to magnesium, 3p6 gets me to argon, and then finally 4s1, 4s2 gets me to neutral calcium atoms. So that's it. So what have I got to do now to make it a cation? To make neon plus, what have I got to do? I've got to remove 1 electron. So where am I going to remove the electron from? I'm going to remove it from the 2p. Okay. To make carbon single plus, I have to remove 1 electron. Where am I going to remove it from? The 2p. To make calcium single plus, I have to remove 1 electron. Where am I going to remove it from? The 4s, the outer one. Okay. This is where it gets tricky. What about adding an electron? I've got to add an electron to the neutral atom. Now, why it gets tricky for neon is I can't go to 2p7 because the p's can only hold 6. So I've got to go to the next orbital, which will be, or the next subshell, which will be 3s. Now, carbon is 2p2. So if I want to add an electron to make carbon minus, I can just put it into the 2p because it's not yet full up. So that can go into the 2p. For calcium, if I want to add an electron to the neutral atom, I can't put it into the 4s. I've got to go to the next orbital over because the 4s is already full up. So I've got to go to the 3d. Remember, it's n minus 1d, and then ns and np. All right. So the next one after 4s, it goes 3d. So I've got to go to the next orbital because the 4s is full to add the next one, so it's going to go 3d. So when you're adding the electron, you might have to start the next subshell, right? If the subshell is already filled up. Whew. Okay, question 9. Oh, it looks like it's the same, doesn't it? Right? Okay, but it's kind of probably going to be like a slightly different set of atoms. Subshell from which the electron is removed, subshell to which the electron is added. So I'm going to kind of speed this up a little bit. So we've got magnesium, zinc, and gallium. So magnesium, zinc, and gallium. So we've got zinc, so it's going to be, I'm going to point out something here that's a little interesting. I'm going to use condensed electron configurations this time. So let's go with zinc. The noble gas that comes before is argon, and then I've got 4s2, and then 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3d, 10. Now I've got magnesium. The noble gas that comes before magnesium is neon, and then I've got 3s2. Okay, and then finally I've got gallium, which is interesting because I'm going to go all the way across the D and then keep going. So the noble gas that comes before is argon, and then I've got 4s2, and then I've got all of the D's, 3d, 10, and then I'm back to 4p, and it's 4p1. Okay, so now I got to think about what's going to happen when I take an electron away and make the single positive cation. What will be the electron that will be removed? And this is where it gets wacky. For the transition elements, you always remove the electron that is in the higher s before you take away one of the D's. So it's going to come from the 4s. You're going to take one electron out of there. Only for the transition elements do you take the s before the D's. So that kind of, otherwise you just take it from the one that's on the end. Okay. Now we've got magnesium is going to come from the 3s. And for gallium, it's going to come from the 4p. All right. Now what about when we add an extra one? Remember what we said? If there's room, we're going to put it just into the last subshell. If that subshell is full, we've got to go to the next subshell. So for zinc, the 3d is full. It's got 10 electrons in it. So we've got to go over to the 4p. Magnesium, we've got 3s2. If we're going to add another one, it's not going to go in there. It can't go in. So we've got to go over, all the way over there to the 3p. Now, for gallium, our outermost subshell is the 4p, so it's mostly empty, so we can just add it directly into the 4p, because 4p2 is still under 6, isn't it? All right? So it takes a little bit of kind of, you know, it's not trivial to get that. All right, what's this one? It says, identifying elements with similar valence electron configuration. So elements that have the same group number have similar valence electron configuration. So we'll see. It says, in the periodic table below, shade all of the elements for which the neutral atom has an outer electron configuration of ms1 nd, where n and m are integers and m equals n plus 1. So it would be something like this. It would be like 4s1 3d10. Like this number is always one bigger than that one. Now, what do we notice about this? They've got d electrons, but they don't have f electrons, right? So let's put our period numbers in. 1, 2, 3, 4, 5, 6, 7. And the ones that have F are all of the ones that are, and also D, are in 6 and 7. So all of these are like out of the question, right? They don't have any P's, so all of those guys are out of the question, right? And they gotta have only one S but 10 Ds. And that's our group where we have the exception, isn't it? That's the copper group here, where they are all of the order of like NS1 or N-1 D10. They're all like that. It's like it, instead of it being like you would predict for copper, that it would be 4s2 3d9. But instead of it being 4s2 3d9, that is actually incorrect. It is actually 4s1 3d10. That is correct. And so the elements that do that are those guys. These ones in the copper group. Copper, zinc, and gold. They're the ones that do that. Now there are there's another group where we see exceptions, and that's in the chromium group, and they are of the order of, they go S1, D5. So you normally are going to get one of these about the exceptions. So the ones that are going to be the elements are going to be copper, silver, and gold. Now, if you look in our module for this week, I'll just quickly log in. 62. Week 2 module, you'll see that I've got an electron configuration table. And you can see all of the ones that have like weird exceptions. Okay, and we're looking for the things that are S1, D10, all right? Okay, so we said copper, and then we got to find silver, there it is, and our other one was gold. Oh, we went one too many. Oh, I just didn't have it, so it's just copper, sorry. So you've got to pay attention to the ones that I eliminated. I did say the right thing. So it is not gold. There we go. Because gold has got the F electrons. There we go. So it's copper and silver. And we could double check it in that table. All right. Good catch, Lee. Okay. Deducing the block of an element from an electron configuration. Okay, so this is pretty straightforward. If it ends in P, it's in the P block. If it ends in F, you guessed it, it's in the F block. If it ends in S, it's in the S block. And who would have thought it, if it ends in D, It's in the D block. So that's really it. And if you want to just like look at the periodic table and see where they are, it goes S, P, D, and F. So you should be able to, you know, figure it all out. So we also have to decide whether it's a metal, non-metal, or metalloid. So we're going to need our periodic table that is divided in that kind of way. So I'm just going to grab the one from the book. I didn't copy all of the bits over. At the bottom of it, it has that. So there we go. We need to get that little bit as well. Okay. So once we've got it figured out, we'll know what's going on. So this is the NS. This is the N-1D. This is the NP. This is N-2F. And remember, these are your 1 through 7 are your N values. Okay. So you've got to read them a little carefully. So this says NS2, but then it does have some Ds. It has a full set of Ds, and then NP. So it's got Ds but not Fs. So what that tells you is that it's between periods 4 and 5 because it's got Ds but it doesn't have Fs, right? So it's got to be P5, so P1, P2, P3, P4, P5. So it's in the halogens. Right, that's your P5 in there. But it's got Ds, right? So it has to be that one. It's got that one, but it doesn't have Fs. So it's just these two guys. Bromine and iodine. That's all it is, because it's got Ds, but it doesn't have Fs. It's not low enough down. So what block is it in? It's in the P block. And what are these elements? These elements are non-metals. Right? They're that green color. So they're non-metals, and it's pretty clearly in the P block. Okay. You've got to be a little careful here. P, and they are non-metals. Now let's have a look at the next one. It's got a completely full S, it's got a completely full D, and then it's got 4 in a P. So it's got Ds, but it doesn't have Fs. So basically it's just one space over from what we saw before. It's going to be in the P block, and they're going to be the two that are over here, right? Because it's got Ds, but it doesn't have Fs. It can't be sulfur because sulfur doesn't have Ds, right? It can't be oxygen, oxygen doesn't have Ds. It can't be polonium because polonium is going to have Fs. So it's got to be one of these two. And so there's a slight difficulty here. One of them, tellurium, is a metalloid, and then selenium is a non-metal. So we've got to select both because it says select all that apply, all right? Check all that apply. So we've got a non-metal and we've got a metalloid. Now, in the ALEKS periodic table, you just click on the symbol of the element and it gives you the whether it's a metal or a non-metal or a metalloid. Okay, so this guy has got 1 electron in an S subshell on the outside of its electron configuration. So its outer electron is an S, so it's in the S block, and then we have to decide what elements these are to decide if it's a metal or a non-metal. And so all of these ones in group 1A have electron configuration that finishes NS1, right? Now, hydrogen is not included here because this guy says, it says in each case, G stands for a noble gas core. So hydrogen doesn't have a noble gas core, so it can't be included. And that is important because hydrogen is a non-metal and all of the others are metals. So if we didn't take into account, if we just said, aha, it includes hydrogen, in the next part of the question, we would have said metals and a non-metal. And that would be wrong because hydrogen doesn't have a noble gas core, so it doesn't apply to hydrogen. It's got to be just metals. All right, I don't know about you, but this has taken a while. I'm going to have a stretch and a swig of my tasty coffee and move on. We've got 3 to go. Let's see how we're going. Periodic properties. Deducing valence electron configuration from trends in successive ionization energies. So what do we know? You've got your outer electrons, and then you've got core electrons. When you remove electrons, it gets harder and harder to remove an electron after every electron. So you remove the first electron, it's not too bad. You remove the second electron, it's tougher. You remove the third electron, it gets harder still. The thing to keep in mind is once you've removed all of the outer electrons, it's really, really hard to remove the core electrons. So at some point you get a big jump and then they start increasing steadily again. All right, and that big jump occurs in between the valence electrons and the core electrons. So what I'm looking for here is where's the big jump? And the big jump in this case is after removal of the first electron. So what that tells me is that this guy has got 1 valence electron. And the fact that it has 1 valence electron tells me that it's most likely in group 1A. So let's have a look at this. And it says it's period 2. There we go. So what we're going to do is go to period 2, group 1A. So period 2, group 1A is it's probably lithium. Right? So lithium has 3 electrons, 1s2, 2s1. When we do IE1, what's happening is that first electron is being removed. That's the valence electron. When we go to, and that the energy associated with this is called ionization energy 1. When we go to remove another electron, we're removing it from the core. And that's breaking up a noble gas helium-like core. And that requires a huge amount of energy. And that's why we see this big jump, this giant jump, more than what we would expect when we go from IE1 to IE2, because IE2 just takes up so much energy to make that happen. So this is most likely lithium. You're just always looking for the jump when you're trying to figure out those ones. Okay. So another problem concerning periodic properties, and this one is about atomic size. It's also about ionic size. They kind of got their naming not quite right here because we've got some ions in there that you can see. So the important thing to remember is this. And you go increasing size. Whoa, wrong property. Decreasing size, decreasing size, or another way of thinking about it is they get bigger this way. Now there are a couple of other things to keep in mind. When we make a cation, we remove electrons. So cations are smaller than their parent atom, right? Because you're taking something away from the parent atom. And then anions are made by adding electrons, so they're going to be bigger than their parent atom. So hopefully that makes sense, right? So putting these 3 bits of information together, we should be able to figure this out. Now we're going to list them in order of decreasing size, and we know that the parent atom is always going to be smaller than the anion, right? So S2 minus is going to be bigger than sulfur. We know that, or we know that already. The question is where does chlorine fit into all of this thing? So let's get a periodic table up and see what we've got. So they get bigger as we go that way. So we've got sulfur and chlorine. So sulfur is going to be bigger than chlorine because sulfur lies further to the left. So sulfur is bigger than chlorine. So it's going to go, we want these in order of decreasing size. Sulfide is bigger than sulfur, which is bigger than chlorine. Okay. All right. Let's have a look at the next one. And again, we see an anion and its parent atom. And we know that the anion will always be bigger than the parent atom. So bromide is going to be bigger than bromine. The question is, where do we put chlorine? So we go to our periodic table. We have a look at where they are relative to each other. Both of those atoms are in group 7A. And chlorine sits underneath, bromine sits underneath chlorine. So that means that bromine is bigger than chlorine. Bromine is bigger than chlorine, and we know that bromide is bigger than bromine. So you put all of that together, what's your order going to be? It's going to be bromide is bigger than bromine, which is bigger than chlorine. All right, the next one is a little simpler because there are no anions or cations or anything like that. We've just got sulfur, aluminum, magnesium. So you just got to follow the pattern. Sulfur, aluminum, magnesium. Okay, so as we go this way, things get bigger. So we need to add them in order of decreasing size, right? So it's going to go magnesium, aluminum, sulfur. There we go. Magnesium is bigger than aluminum, which is bigger than sulfur. So always be really careful that you get the order of the ranking in the correct direction. Okay, last but not least. So what are we doing here? 2 sets of ionizations are shown in the tables below. Complete the tables by ordering each set of ionizations by increasing amount of energy required. In other words, for each set, choose one next to the ionization that would require the least energy and 2 next to the ionization that would require the next least energy. So what we're going to do is we're going to list them of increasing ionization energy. So we need to know the pattern for this, right? What is the pattern? How does ionization energy, and this is ionization energy 1, because we're only adding 1 electron or removing 1 electron. How does that vary? And what we know is that it increases left to right, bottom to top. And there's a couple of ways of thinking about this, but basically what you want to recognize is that as the atoms get smaller, the electrons are closer to the nucleus, and so they are harder to remove. And that makes total sense, right? So the bigger the atom is, the further away the electrons are from the nucleus, so therefore it becomes easier for them to be removed. And your biggest atoms are down here and your smallest ones are up there. So really we just got to pay attention to our periodic table and keep this trend in mind. So we'll put that there. Wow, that's not what I wanted. Let's not. Let's see if we can move it over there. Okay. So what we know is that ionization energy 1 increases like that. Okay, so our first 3 elements were radium, Ra, bismuth, which is way over there, and then oxygen, right, which is underneath my arrow there. So it increases as we go this way. So what one, we're going to list them in order of increasing. So obviously radium is way over there. So it's going to go, radium is going to be number 1. All right. And then our next one will be bismuth, number 2. And then oxygen is up there, and that's going to be number 3. Now, where's francium? Francium is even more, or even less, lower ionization energy than radium. In fact, this makes francium incredibly reactive. So that's going to have very low ionization energy 1. Then aluminum is there, and then we've got carbon there. So we just have to follow the arrow, don't we? So it's going to be aluminum and then carbon. Now the general trend is that metals have low ionization energy, non-metals higher. Okay, so you have a little kind of, well, you know, there's no confusion here, they're all clear cut, but the non-metals should have higher ionization energies than the metals. Metals love to lose electrons. That was kind of easy because they were all, you know, in 1, 2, 3, 1, 2, 3. Okay, so that concludes this video where I work through each of the objectives. It's not trivial, you know, there's a decent amount of content, but it's not too bad, you know. You can do it slow and steady. My experience is that the biggest difficulty is with dealing with the Heisenberg uncertainty principle problems. So you just take your time when you're working through those, and I'm sure you'll do great.